Good morning, good afternoon, good evening to all of you. Welcome to the KiboCUBE Academy session online. So today we will be covering a lot of different things. So I'd like to move on and start the webinar. So before we begin, I'd like to just mention a few things. So please use the Q&A box to ask any questions. Please do not write in the chat and raise your hands. We will not be able to give you access to speak up. So if you have any questions, please use the Q&A box. Please don't use the chat. Don't write to the host and panelists. We are over flooded with messages sometimes. So if you have any questions, please put it in the Q&A box, and then we will refer to it at the Q&A session in the end. Second, please answer our questionnaire form that we will be putting in the chat box later on. So my colleague Wenbin will be active in the chat, providing you with useful links related to the webinar, related to the content, but also link to our questionnaire form. So please answer that before you leave. We would really like to hear your feedback. And last but not least, if you are on social media, please use the hashtag Access to Space for All, KiboCUBE, KiboCUBE Academy to help us promote this webinar. We are active on Twitter/X, Facebook, LinkedIn, and Instagram. So today's agenda is basically covering one important topic, which is the systems engineering for micro, nano, and pico satellites by Dr. Shinichi Nakasuka. And after that, we will dive into the Q&A. But before I give Professor Nakasuka the floor, I just wanted to mention KiboCUBE Academy in the sense that we have 3 new on-demand pre-recorded lectures on the KiboCUBE Academy website. It's the ones that are marked in red. So we have 3 new lectures. So if you are interested, please have a look. Also, maybe some of you have noticed, but we have updated our KiboCUBE Academy webpage to give you a bit more visibility on the different webinars we have. And yeah, the content is all the same, but I just wanted to mention that KiboCUBE Academy has been updated in that sense. And second of all, I just also want to mention about KiboCUBE again. I believe most of you, or maybe many of you, are interested in applying to the KiboCUBE round that is open for applications right now. So I just want to mention again where you find the documents and all of that information. So basically, go to our UNOOSA Access to Space for All website. KiboCUBE is under the satellite development track. So you go to the satellite development track and it's a hands-on component. So go under there where you will find KiboCUBE, and then you will be taken to the the KiboCUBE index page, the main page. There you have to scroll down a bit and go to the rounds page where you will find all the important and related documentation. We have all the webinar information there. You can jump to the KiboCUBE webinars and the KiboCUBE Academy webinars. And we have the announcement of opportunity document, of course, the application template form, the GEM payload accommodation handbook, which is the most important document that you would need to read. And we have these other reference materials as well. So all I can say is really read all of the documentation carefully. Watch the on-demand pre-recorded KiboCUBE Academy webinars. This would be a massive help. And of course, the live sessions, like the one today, it's all recorded. The presentations are there, so have a look. And of course, make sure to submit the application form for KiboCUBE by the deadline, which is the 31st of December. Just to give you an image on the schedule, as you can see, we've done many webinars to help you support the application process, and we are here at the KiboCUBE Academy webinar in November. And after that, you have another month or 2 to fill in the application form. And from there, we will be going through the selection. We will be announcing the shortlisted teams in February. After that, we will be asking the teams to do an interview. We will be asking them to submit some updated information, review and confirm the legal agreement. And then in the end, we will announce the winners of this round in June 2024. After that, you can see there's a lot of things that would need to happen, which is, of course, the development, handover and transportation, the launch, but also outreach and publication phase. So this is what the schedule for this KiboCUBE Academy, this KiboCUBE round will look like, and we really hope that this webinar will help you get there. So with this, I'd like to introduce Dr. Shinichi Nakasuka, who is the professor at the Department of Aeronautics and Astronautics at the University of Tokyo, and who is a member of UNISEC, to start his presentation. Dr. Nakasuka, you have the floor.
Thank you. Hello, everyone. My name is Shinichi Nakasuka. today I'd like to talk you about a systems engineering for micro, nano, pico satellite, of course, including the CubeSat. So before going into the main topics, let me introduce myself as well as the activities of our laboratories. So I have been working for the University of Tokyo for about 30 years, and I also have been working for the UNISEC in Japan. And not only the university job, I'd been working for the Space Policy Committee of the Cabinet Office of Japanese government until 2022. And my main research topics include the micro, nano, pico satellites, novel space systems, guidance, navigation and control, autonomy and intelligence for space systems. So let me show the activities of our laboratory. We succeeded in developing and launching the world's first CubeSat in 2003, which is called the Psi-4. And the second satellite, Psi-5, was launched 2 years after. And this satellite has been surviving in space for more than 20 years. And we could obtain this kind of the very beautiful picture of the Earth for over 20 years. So maybe as you see that the color of the pictures has been changing from blue to yellow. So at the time when I first saw this sequence of the color change, I was very much afraid that the color of the Earth has been changed. Of course, that is not true. So this is because of the degradation of the lens of the camera, because the lens was made out of plastic. So in this way, if your satellite survives in space for long years, you can get various information, including the environmental effect. So another environmental effect or long life effect is looking like this. It is a battery voltage. So the horizontal axis shows the elapsed time from launch, and the vertical axis shows the battery voltage. And maybe as you know, that when the electrical current is flowing out of the battery, its voltage will be going down because of the internal impedance of the battery. So this difference is a kind of show the internal impedance. And as you see that as time goes by, the internal impedance of the battery is growing up. So this is another effect of the long life of the satellite, and maybe you can get this kind of the battery degradation information if your satellite survive long within the space. So this is another very important information to be utilized for the next satellite program. Okay. And starting from the world first CubeSat launched in 2003, called the Psi-4, we have been developing the gradually larger and more sophisticated satellite like this. And initially, we are doing the education and experimental satellite, and then we challenged the space science, that is obtaining the very precise map of the stars in collaboration with National Astronomical Observatory of Japan. Then we challenged Earth observation with Hodoyoshi 134, and the technology demonstration to demonstrate some technology like a communication or a water resist jet. We also have been supporting the foreign country to develop their own satellite, Micro Dragon for Vietnam and Ruasat-1 for Rwanda, which was launched in 2019 using Japanese Epsilon rocket. And the entertainment satellite. And also, recently, we have been focusing on the deep space exploration. The first one is Procyon, launched in 2014. And last year, we launched Aquarius, which is a 6U CubeSat. And recently, we are focusing on the 6U CubeSat, and one of the 6U CubeSat was launched in just January. So, in total, we launched 15 satellites. And more than 125 students were trained in this kind of the practical space project, who have been working very actively after graduation. So this is the overall history of our laboratory. Let me show the example of the satellite developed within our laboratory. One is a Hodoyoshi 3 and 4 launched in 2014. These are the Earth observation satellites, and we have this kind of the target. We should develop this satellite within $3 million US and within 2 years. And that was successful. And this satellite has a very good capability of the downlink speed and power and attitude control capability, which are suitable for Earth observation as well as space science. Even this kind of the very good satellite can be developed within the university capability. So let me show the several pictures taken by these satellites. So each satellite has 5 cameras. So starting from a very low resolution to high resolution. So this was pictures taken by the wide angle camera. Maybe you can see where it is. And the highest resolution camera was a 6 meter, which was implemented on the Hodoyoshi 4. Maybe as you can see that agriculture field or rice field was seen one by one. So if you continually monitor this agriculture field with this satellite, then you can guess something like diseases on the agriculture field or the lack of the water. And during the mountainside, this satellite can detect the landslide or other disaster. So in this way, even this kind of the small satellite developed by the university can be effectively utilized for the various applications. The important thing is that it is not good for you to develop only one satellite, and in that case, maybe you can monitor this area every, for example, 10 days or 20 days. That is not enough. So if you launch many satellites all together, and these satellites will monitor these areas one by one, then you can obtain about everyday coverage or every 2-day coverage of the same area. That is a concept of the small satellite constellation. Now, in the world, many types of the small satellite constellation business has been occurring. So that is a current trend in the world. Based on the Hodoyoshi technology, we challenged the deep space exploration probe, and we successfully launched the world first 50-kilogram class deep space probe called the Procyon. That was launched together with Hayabusa 2 at the December 2014. And we experimented many things in the deep space. Deep space means it's escaping from the Earth's gravitational field, like communication or navigation, guidance, and control. Not only such kind of the engineering experiment, we could obtain various scientific results, like monitoring the Earth's hydrogen emission or hydrogen around the Churyumov-Gerasimenko comet, which was the target of the European Space Agency's Rosetta mission. And our second deep space probe is called the Aquarius. That is just a 6U CubeSat, very small CubeSat, which is just 11 kilogram. And the student has been working on this. And last year, we successfully launched this by using the Artemis 1 rocket from United States. Maybe as you see that, very much, satellite is congested. Many things have been packed into these satellites. So this is very important, and the Japanese people are very good at making this kind of the very condensed or packed satellite. So you know why? This is because we are living in a very small house. So this is good thing, good skills of the Japanese people. And as I said, this satellite has finally launched by the Artemis 1, that is a lunar rocket from the NASA in last November. And now it is flying towards Earth-Moon Lagrange point 2. And because the amount of the fuel to be implemented in the satellite is very much limited, so we are making this kind of the very complicated trajectory, utilizing the swing bys of the Earth and the Moon, and going to the Earth-Moon Lagrange point. And when our satellite flies very near to the Moon, it could successfully obtain the pictures from the Moon. It is like this. It is about 5,000 kilometer altitude from the moon. Another very important application of the satellite is to get a weak signal from the ground. For example, if you put several sensors on the ground, if there is no ground infrastructure of the communication on the ground, if you want to get the data from this sensor, you should go there. That is time consuming, and sometimes it is very dangerous in the case of the disaster. So if you can put a very small transmitter to these sensors, and this transmitter send the data into the sky, then the satellite can collect such kind of data when it flies over that area. So this kind of the mission is called the store and forward. And the store and forward can collect ground information automatically. So that is a very important infrastructure. And the important thing is how to send the data with very low RF power to the satellite. So we have been elaborating on this, and finally we could obtain 8 milliwatt very low RF power, reception from the satellite. And this satellite called the Tricom-1R, that is a 3U CubeSat with a 3 kilogram weight, was launched into the space in 2018 using the Japanese SS-520 rocket like this. And we succeeded in the transmission to the satellite. And based on the success, we are now trying to make an international network of store and forward together with, for example, the Rwanda and the other African country, which is now being discussed. Recently, as I said, we have been focusing on the 6U CubeSat, and we are developing the very versatile 6U CubeSat bus. And one application is to utilize it for the Sphere 1I satellite, which has been developed in collaboration with Sony and JAXA. And we developed the bus and the system integration, and now the students are operating this satellite. And its mission is to make the customer to operate satellite directly to capture various images such as Earth, stars, and so on. And it was developed within 2.5 years and launched in just January. And let me show the pictures taken by this satellite. As you see, so it is pictures taken by the Sony camera. So Sony produced a very good camera. So it produced a very beautiful pictures of the Earth or moon like this. And also we could obtain this kind of the moving video taken by this satellite camera. Okay, so this is the end of the introduction of our laboratory's activity. And we have been accumulating various technology of the systems engineering for micro, nano, pico satellite through these kind of the university programs. So based on that, I'd like to talk you about the systems engineering required for the micro, nano, pico satellite with G's story, subsystems and their relationships, possible causes of CubeSat failures, why are space systems so difficult, and the important thing is to make your satellite die hard. Start with a very simple satellite. That is a key point. And study and training before building a CubeSat. What kind of the training should be required before the CubeSat? And define the target outcome of the project. And I'd like to conclude my talk. First, subsystems and their relationships. So this shows a typical satellite subsystems. Maybe you can see the onboard computer, OBC, and the memory, and the bus, information bus. These are called the C&DH, command and data handling system. We need a communication system because the satellite is far away from us, so we need to communicate with them. One is uplink. The satellite side has a receiver to receive the uplink command from the ground, and the transmitter to send the data to the ground. That is called the downlink. And sometimes we need a computer inside of the communication system. And we need some sensors. Sometimes we need sensors for the internal information like voltage, temperature, and of course we need sensors for the outside information like a sun sensor, star sensor, GPS, and so on. And actuator. Actuator means something which can move or rotate the satellite. Thruster, magnetic torquer, and reaction wheel, and so on. And sometimes by combining these actuators and sensors, we can configure AOCS, attitude and orbit control system. That is also the very important subsystem. And the mission subsystem is a main part which can actually perform the missions. Sometimes sensors or experimental system, camera, or transporter will be required for various type of the missions. And these are something like electronic type of the subsystems. And in order to provide power to this system, we need a solar cells, battery discharging and charging cycle, and so on, which is called the power system. And in order to keep the temperature of the satellite, we need a thermal control system, including the MRI, cooler, heater, and so on. And the structure and the mechanism system will required to constitute the satellite, and also moving something like a solar paddle or antenna and so on. That is called the mechanism system. And this is not the satellite subsystem, but the ground station is another very important subsystem. Okay, so these are the total configuration of the typical satellite. We need to make a very good design for the satellite subsystem interfaces. For example, we should first define how many and what kind of CPUs are to be used for usual CPU or FPGA and so on, and what kind of the performance level we need. Such kind of things should be defined first. 1 or 2 OBC for main functions and attitude control, or we need more, and so on. And also we should make interface design between C and DH, command and data handling system, and other subsystems. What kind of the information line we need, we would like to use. For example, RS-232, 422, or middle standard, or SpaceWire, Canvas. There are many type of the information line. And the interval of data exchange between C and DH and other subsystems, and how much amount of the data to be transferred between them, and what kind of the data to be transferred between them. That is also the item to be designed. And the next one is interfaces between C and DH and communication subsystem. So the communication system should downlink a large amount of the data sometimes. So in that case, such kind of the large volume of data had better be stored in the C and DH side or in the communication side. So you should define like that. And the interfaces between C and DH and the mission subsystem. Also, the mission, like a camera, will generate a lot of data. And in that case as well, such kind of the large amount of the data had better be stored in the mission side or in C and DH side, and so on. And also, how will mission components be controlled, and how are those data received is another item to be designed. And between power subsystem and other subsystems, there is many interfaces will be required. So the important thing is that what kind of the reset means a power off on function is to be implemented. That is very much related to the survivability of the satellite. So I'd like to go into detail later. So these kind of the interface should be defined initially. It is called the top level design of the satellite. So this design will decide the satellite architecture. So you should do this in the initial part. Possible causes of the CubeSat failures. So failure, we don't like it, of course, but still we have many failures. So this, statistics is based on the study of St. Louis University like this. And maybe as you can see, the launch fail is about a 6.3%. So it is not a fault of the satellite, but the DOA, dead on arrival, that means that the satellite did not function after release from rocket is 80, many large amount of the, portion. And the early loss died soon after operation started. It also has a large portion. So the only successful mission is about a 35%, and the still failure rate is about a 50%. It is a very big amount. So the thing for us to consider is how to reduce this kind of the failure rate. So that is a very important technological issue. So these show the frequent causes of failure and the countermeasures. What should you take special care of? Radiation is a very big source of the failure. It causes electronics failures in many satellites. So in order to make a countermeasure for this, we should use space-proven parts or conduct radiation tests during early development phase. So if you develop a satellite and in the later phase of the development, we found that your, OBC, CPU is very, subject to the radiation effect. That is too late. So in the initial phase, you should make such kind of the radiation test to select which component to be used. And the next big failure cause is electric power subsystem. So it may fail to provide power and or battery voltage gets very low and cannot be recovered. In that case, satellite will die. And how to make a countermeasures. So you should design satellite behaviors under even the low battery voltage. So once your battery voltage gets very low, then after the solar power generation, it will recover. So you should make a treatment that your system can do such kind of the recover from low battery voltage. And also, you should make solar power generation possible in any situation. I'd like to show you later. And another big source of the failure is a communication subsystem. So it fails to communicate with ground station because of communication component failures or insufficient RF power or electromagnetic interference. So this kind of the thing may happen in your satellite. What kind of the countermeasures will be required? So you should implement backup systems. So that is a redundant receivers and so on. And also you should calculate the link equation correctly and add enough link margin. And you should conduct ground test using your EM or FM in a realistic situation. And you should find and consult with communication technology experts because the communication technology is very difficult to acquire. So maybe it's better for you to find out the person who has a very good skill or experiences of the designing and developing the communication system. Okay, so now I'd like to show why the space systems are so difficult. Maybe as you understand, space is a very harsh environment. Vacuum environment is very harsh because it vaporized many, glue or painting. And the cold welding occurs. Cold welding is a very dangerous event. For example, if you, put the two axes and the, two metals like, aluminum all together. And in the atmosphere, maybe there is some layer of the atmosphere between these two materials. So it cannot attach. But in the space, this air will be excluded. And so these two aluminum will be get together. we cannot remove these two aluminum anymore. So this phenomena is called cold welding. That is a very dangerous phenomena, and many failures occurs in the past because of this cold welding. And also the friction, electric discharge, and the change of material may occur within the space. So change of the material means, for example, as I said before, the change of the color of the plastic lens of the camera. That may happen in space. And the radiation. Of course, radiation make a very bad effect on the electronic parts, malfunction and breakdown sometimes. It is called the SEE, single event effect. One of the SEE is a single event upset, which means a change of 0 and 1 of the information of the semiconductor. Or sometimes the semiconductor will be breakdown, which means single event latch up or single event burnout. If that things happen, the electric part will never recover to the normal state. So you should avoid such kind of the radiation effect. And the another very difficult and important radiation effect is a total ionizing dose. So it is called the total TID. And in this TID, the semiconductor will gradually degrade it, and at some point it suddenly does not move anymore. For example, after 2 years exposure to the radiation environment and space, it suddenly gets failed. So that kind of the thing is called the TID. So for the satellite design, or especially the semiconductor selection, you should consider this SEE, single event effect, and total ionizing dose, TID effect, both. As to the thermal environment, so the large temperature difference may occur in the Earth's orbit. So if for example, aluminum is shined by the sun, then its temperature will go over 40 degrees Celsius. And if it goes behind the Earth, and then the temperature quickly goes down as low as minus 70 degrees Celsius and so on. So that means the surface of the satellite has a very big temperature difference. So you should make a proper treatment of the surface so that inside of the satellite will not have such kind of the large temperature change. Maybe you should keep the inside of the satellite like a 0 degree to 30 degree and 50 degree and so on. Launch will provide the satellite with a very big vibration shock acceleration load. And so your satellite should endure such kind of the load. And the distance is another very difficult thing. So the long-range communication will be required over 500 to 2,000 kilometers. It's a very, very long distance. So your communication system should be carefully designed in order to have such kind of the long-distance communication capability. And the others will include atomic oxygen, plasma, and so on. But I think the most difficult thing for the space system looks like this: non-maintainable system. That non-maintainable system. That means once launched, you cannot touch your satellite anymore. Okay? It is non-maintainable system. And in that environment, sometimes the satellite has to survive in space for more than 10 years without any human interactions. So what you should do? Imagine all the possible events and anomalies which may happen to your satellite and prepare countermeasures for them. So the imagination is very, very important. And conduct ground tests in various settings to ensure proper functions of your satellite in the space environment in various operation modes. So you should do this kind of the thing in order to do your satellite, in order to survive your satellite in space, because it is non-maintainable system. Okay, so then this is a very important topics: how to make your satellite die hard. So the way how to develop a satellite has some technology, has some strategy to make your satellite reliable in space. From mission creation, at the time we will do some system concept design. And then in the initial phase, we are doing the various trial and error of the detailed design of the satellite, which can realize your mission. So this phase is called the breadboard model. During this phase, we will do the various tests like radiation test, simple function test on CubeSat, and so on. And gradually, we are getting the detailed design of the satellite. And at the end of the BBM phase, we will have the preliminary design review, PDR. So that assure the feasibility of the current design to realize your mission. And then engineering model phase start. So the objective of this EM phase is to assure your satellite functionality in the space environment. So in order to assure that, we need to do various space environment tests, including the vibration, shock, thermal vacuum, and so on. And then at the end of the engineering model phase, we will do the CDR, critical design review. That is a point when we fix our design. And then we start the fabrication of the flight model. And even in this flight model phase, we should do several tests like a vibration, shock, thermal vacuum test, but with less, launch load. So in the EM phase, we are doing the, very strong load, which is called the qualification test level. But in the flight model, in order to avoid the fatigue of the flight model, the load will be a little less, which is called acceptance test level. And then at the end of the flight model, we will do launch readiness review. That means now that everything is done and we can wait for the launch. So we should review like that, which is called LRR. And the launch and operation will start. This kind of the, one way design development process is called the water flow project management. And we should do a lot of ground tests in order to assure the proper functionality of the satellite. And this kind of the return to the previous stage should be avoided as much as possible, because this kind of the returning to the previous stage will result in the additional cost or additional time of the development. That is not good. So we should avoid such kind of the return to the previous phase as much as possible. That is a very important, I can say strategy. So let me show these several pictures for the satellite development. So once the component are ready, then the students put the component on the table, connect by the wire, and make a functional test of these components. This test is called the table stat test. That is a checking of the proper functionality and the connections between components. After that, the student implementing these components into the structure. This is called the satellite integration. Maybe you can see the many harness wire. So how to make a wire routing is another very important topics within this phase. And then when the satellite is ready, we should bring this satellite to the test site and to do the space environment test, like a vacuum test, vibration test, and thermal vacuum test. So you should do this kind of the test in the engineering model phase as well as the flight model phase. So in the design, we can implement the survivability of the satellite as much as possible. How to realize a certain level of reliability with limited resources. So this is a very big issue for the CubeSat and small satellite, because we don't have a large size and the power is very much limited. How you can realize a certain level of reliability within such kind of the resources. So this is an example of the strategy we took in our first CubeSat Sci4. In the OBC system, we have the one PIC processor, PIC 16F processor, and the transmitter TX also has the one PIC processor, and the CWRX system has another PIC processor, and these PIC processors are doing their own job to manage each subsystem, OBC, TX, and CWRX. And in addition to that, they are watching the behavior of other subsystems. And if something wrong happens, such as a hang up, then, for example, the OBC, PIC can reset this power line to the TX and also this power line to the CWRX. So if the TX system hang up, then it will be resetted by the OBC. Okay, then usually the TX system will go back to the normal state. So this is the same as what we do when our PC or laptop computer hang up, and usually at the time we will make a reset of our PC and so on. So this is the same thing which has been done in the satellite. So another one is excess current monitoring. If the SE, single event effect, occurs for a certain subsystem, quickly large amount of the current is flowing, then that current should be cut suddenly in order to avoid the failure of the component. So that kind of the thing also can be done by using this line. For example, the OBC can reset this line and so on. So this kind of the mutual monitoring and the SE monitoring is very important to make your system survive in space. Die-hard system is essential. Mutual monitoring or reset operation and monitoring excess current against radiation effect. You should implement such kind of the thing in your satellite system design. In our third satellite PRISM, we did very different things. So we already proved the proper functionality of PIC 16F processor in space by using our Psi4 and Psi5. So we can rely on this. We can trust these processors. Then what we did? Okay, so this two processors are watching the behavior of the other computer like H8 or SH2, which were new to us and which has not been proven in space. And so these are the very high functionality, but we cannot rely on this. So the PIC 16F processor watching the behavior of these other subsystem CPU. And if something wrong happened, it reset this subsystem. But we did not implement a function that this new processor will reset PIC 16F. So PIC is a kind of the hierarchical monitoring structure. Combination of high performance but not space problem processor like H8 or SH2 plus low performance but space proven processor like PIC 16F. This combination is very, very useful and effective. And because of this architecture, the PRISM has been working in space over 16 years. 15 years. Okay? And the example of useful reset mechanism, another very important or thoughtful idea to use a counter circuit for a reset mechanism. For example, in your satellite may have the receiver, okay, to get the command from the ground and the OBC. And in order to make a reset of these, component periodically, we put a counter circuit that is made not by the CPU, but a hardware logic. And that means it is a very high reliability. And this counter circuit will count up. And if the count will come to a certain value, then it will reset this receiver and OBC. That means this resetting of the receiver and the OBC happens every 1 week or 3 days and so on. It depends on the number of the threshold of the counter circuit. Okay, and so in this way, these two very important components will be reset periodically. But that is not good because we want to keep the behavior of the OBC. Okay, So we don't want to do such kind of the reset. So what we should do? So if we send a command to reset the counter circuit, we can send a command to reset the counter circuit, and this command will only be valid. We will only be able to reset the counter circuit when the receiver and OBC are active. That means if this counter circuit is counted down, then we can assure that the receiver and OBC are active. So this kind of the treatment is very effective. Counter circuit counter reset, okay, of this counter circuit is possible by command from the ground, which is only possible when RX receiver and OBC are functioning correctly. So in this way, we can make the how to say periodically reset of this processor. And if we don't want such kind of the periodical reset, we will do this kind of commanding to counter reset. So this is a kind of the technology which is very effective for the to make your satellite survive in space. Another very important consideration is the modes. Okay, so for example, a satellite has passing through the various type of the mode. Release from the rocket, then the release switch automatically turns on the satellite system. So the satellite is moving. That is the initial mode. And the satellite is subject to unpredicted tumbling, and the CPU and the transmitter is only on at that phase. And then we should go to the mission mode when the satellite can do actual mission like Earth observation or communication and so on. And between this, we sometimes may have this kind of additional mode, some acquisition mode or mission standby mode. So this mode is very similar to the mission mode, but the difference is that the attitude to get large solar power generation is assured in this mode. Sometimes the mission mode, the attitude is not good to obtain enough solar power that is larger than the power consumption. In that case, by keeping the satellite within this mission mode is very, very dangerous because of the power balance. It may reduce the battery voltage, and finally it may die. So if that is the case, then you should add this kind of the mode when the solar power generation is larger than consumption, and keep the satellite usually in this mode. And at the time when some mission occurs, then it goes to this mission mode, and after the mission ends, then it goes back to this mode. So this kind of the power management should be done. In addition to that, if something happens in the satellite subsystem or battery voltage gets very low, then it is very dangerous situation of the satellite. So in that case, it should go to the safe mode. Automatic transition to the safe mode should occur. And in this safe mode, the minimum components are on. So that means the power generation is larger than power consumption. So this kind of the safe mode should be prepared. And this red part is made usually by applying command or automatically. For example, if we have this kind of the condition to transfer from initial mode to acquisition mode, and then this occurs, then we can send a command to the satellite to transfer from this mode to this mode. In this way, mode definition and transition design would be very important technological issue. So let me show more detail about a safe mode. Safe mode looks like this. Sometimes anomaly situation affects satellites such that the battery voltage drops to very low. The downlink telemetry includes such data that cannot be explained. Something happened in the satellite. The satellite attitude motion is strange. Something happened in the satellite. And in that case, the maximum survivability can be obtained by making your satellite transfer to safe mode, which assures the minimum power consumption, and the power generation is larger than power consumption. And at that time, we need to collect the satellite information as much as possible and analyze what happened in the satellite and send a command to repair this satellite. So we need sufficient data for analysis of the cause of anomaly. So that kind of the data should be downlinked. Safe mode should be designed such that it can be entered even when the ground station cannot communicate with your satellite. So the satellite mode can be set a survival mode. That is very important. Communication system is also very important subsystem, especially the center line that is from ground station, receiver, and OBC. That line is called center line. That is very important. And we should use reliable CPU inside the communication receiver. And it is highly recommended that command from the ground can reset component without using the OBC, because sometimes OBC may fail. In that case, only the receiver can reset everything. That is very, very important. And design an effective antenna. Antenna should be stowed during the launch and take a proper shape after deployment. And even if any component fail, some information should be downlinked to ground. So, for example, even if you cannot utilize the S-band downlink, CW beacon can be used as a backup for telemetry downlink. So this is important because if no information is downlinked to the ground, we cannot analyze the cause of the failure, and we cannot feedback the result of this project to the next project. So some information should be downlinked to the ground. And the functional redundancy is another very important matter. If, for example, if you use S-band for housekeeping and X-band for mission data, in case of S-band failure, X-band communication line can also be used for downlink of housekeeping telemetry. You should make such treatment as a backup of your system. So the center line looks like this. In our previous shown prism system diagram, from ground station to receiver. So these are the very important. So we make a redundant system, and from this receiver to the main OBC. So this line is called the center line. You should make reliable this center line. Enabling solar power generation in any altitude is another very important consideration. So if your satellite has a solar paddle like this, then of course you can get a very large solar power generation. But the power generation is possible only when altitude control works properly. That means if the altitude control is not good, then the sunshine is not going to the surface of the solar paddle. Then we cannot obtain any solar power generation. On the other hand, body mount type, in this case, we have only limited power generation. That is, shortcomings. But the power generation is possible regardless of altitude. So, in the very simple satellite, for example, one CubeSat body-mounted cells on all the 6 surfaces are recommended. We did for our satellite as well. Start with a very simple satellite. This is very important, strategy. In your first project, start with a simple and easy to realize type of the mission. And if you still have additional time and budget, then try to consider additional mission. That is, keep it stupidly simple. That is a very important keyword. Functioning CubeSat and space itself is an important mission, even if it does not have any sophisticated mission. Functioning CubeSat itself is a very important mission. So, in order to realize that, you should pursue survivability as much as possible. And find out and pursue what you can do with your limited resources, not aiming at too high a level. So high level mission should be pursued after your first success. So please start a low level and simple missions. And try to find external supporters like a technical consultation, testing facility, donation, and so on. And promotion your activity to the general public is also very important. you should find a very good supporter in the external environment. And study and training before building a CubeSat. It's not good to quickly start the CubeSat, but before that, you should learn many things. For example, the basic knowledge on mathematics, physics, rigid body dynamics, and so on, printed circuit board design, or orbital mechanics, attitude dynamic control, and so on, which you can learn from the text. And also, in addition to that, you need to do some practical training using real project. So for that objective, I'd like to recommend you to do the CANSAT. That is an excellent tool. And through the CANSAT, you can learn project management and teamwork, system level design, how to make a die-hard system, and ground test and operations from the ground, and so on. So you can learn many things in the CANSAT. So I'd like to recommend you to do that. And another very important thing is that at the time when you launch your CANSAT to a certain altitude using a rocket, then once you pass your CANSAT to the rocket engineers, you cannot contact it anymore. So this is the same situation as the satellite that is a non-repairable system. So you can learn how to design a satellite which is non-repairable system as well. So this kind of the CANSAT has been used in Japanese university training for long years, since 1999. Various type of the CANSAT has been developed. So starting from the 350 milliliter CANSAT, and then the many universities are going into the a little larger CANSAT called the open class, and these CANSAT will be launched by the ALICE rocket provided by the amateur rocket group in the Nevada. So let me show the example of the launch of our CANSAT. Aeropac amateur rocket group lifts our CANSAT to the 3.6 kilometer altitude in Nevada. And during the descent, which will take about 15 minutes, various experiments are to be conducted. So every year the students bring their CANSAT to there and then test their CANSAT in the real environment. And so this is one way to launch your CANSAT, but there are several ways to launch your CANSAT. For example, using the helium balloon to a certain altitude, not so high, but 100 and 200 meter would be possible, or drone or UAV are also being used recently, or in the simplest way is to drop your CANSAT from a high building. And in the CANSAT, we have been doing a very interesting mission called the comeback competition. In this competition, we put target point in the desert, and the CANSAT should go autonomously to this target point, and the CANSAT which comes nearest to the target point will win the competition. So the GPS information is a very important information. Okay, and various type of the CANSAT have been appearing, like a parafoil type, or fixed wing type, or drone type, or a robot type. Okay, so it's a kind of the fight between the flyback type versus robot type. Let me show the example. So our student, a University of Tokyo's student, joined this comeback competition in 2017, and they made a very good, approaching to the target until 1.34 meter using the GPS information. But as you know, the GPS information is not so accurate. Accuracy is something like a 3 meter. So the rover cannot move nearer to the target. You only using the GPS receiver. So they switched camera-based navigation at this point, and try to recognize the target and try to move toward the target. But it did not move at this point. Please guess why. So this is because the sunlight is coming, and the rover could not recognize the target point. But they have the second chance after 2 days, and they made a lot of trial and error at the site in order to solve this problem. And after 2 days, they succeeded in achieving the 0 meter to the target. So, and won the competition. So this is a kind of the problem solving. And this kind of the problem solving is also trained in the CANSAT as well as the satellite project. In order to make a very good training, in order to obtain the very good training, strong motivation is very important. In this case, strong motivation is coming from the sense that we want to win the competition. So this kind of the strong motivation is very important to be trained in the program solving. So program solving training is very important because life is full of problem solving. And for most of the problems, there are no answers yet. Most of them cannot be solved by knowledge and skills in a single area. You should combine and integrate many areas, skills, and knowledge. And setting goal by yourself is also very, very important. And satellite and CANSAT development provides excellent opportunity of training for problem solving because no correct answers exist before, cannot be developed only by single technological areas, and you can set your own goals for your project. Okay, so you can get training, as I said before, only when you have strong desire, strong motivation to solve the problem. And the satellite and the CANSAT development will provide such kind of the motivation to the students. So that's why this kind of the project is very important for the problem solving training. And the failure is also the very important material of education. What may happen in this? So parachute and the main body were separated and the main body crashed on the ground. It happened in 2000. So the student can learn many things from failures. And the engineers should experience failures while the project size is small. That is very, very important. While the project size is small. So CANSAT is a very appropriate level of the size of the project where you can make failures. So I'd like to recommend you to do this kind of the CANSAT training. And as to the CANSAT, UNISEC has been providing the CANSAT education, which is called the CLTP, CANSAT Leader Training Program, for this kind of the years. And we still have this kind of the CLTP. So if you are interested, please contact the UNISEC. Finally, I'd like to show the define the target outcome of the project. Maybe there may be several various options for satellite development. Now you can buy the CubeSat component very easily from the website. And how to mix this kind of the purchased components and the ones of your own design. So by doing this, there are several type of the options. The first one is like this. You assemble a purchased component with a fixed mission. So that is a kind of the kit, and then do ground test and launch operation. Option one, that is some option to this choice is that you add one original mission, only one original mission, in addition to the kit with your own designed component. And the second option is to create your own mission, buy components to realize your mission, and do ground test and launch operation. And option to this will include the design, fabricate a few components, and design, fabricate all the components. So you should find out adequate option considering your team's expertise and your target outcomes. Then what we did for our CubeSat is option 2 and 2. Okay, so this table shows what you can learn in each option. The vertical show the option, and the horizontal show the what kind of skill or experience you can get in your option. Mission creation, architecture design, system analysis, subsystem design, project management, and test and ground operation, and so on. The upper is easier and the lower more difficult. So if you only buy a kit and make it and launch, then it's a first one. Only you can get a small effect in the project management and the test. And of course, you should operate your satellite so the large effect will occur in the ground operation scale. And the one, you made your own mission, and you buy some component to realize your mission. Then we can add several small effect at this point. And in the second, you develop your own mission and so on. So we have a large effect, in the many field. And but we don't in the option 2, you do not, fabricate your own component. So the subsystem design has some effect here. So it is, blank. But if you make only one component, then you can have a small effect at this. Subsystem design would be possible. So there are many large L and small s here. And if you make everything, then everything you have large L. But as I said before, considering your expertises and your target outcome, you should find out appropriate level. That is very important. And I'd like to recommend two options, 1 and 1 and 2 1. That is a two recommended option. That means you purchase the kit. So most of the mission is already designed, but you design and fabricate one original mission by yourself. And the another one is the original mission you should design with purchased component. But you will use almost all the subsystem. But you only design one or two, very few, subsystem. Then you can get a S here. So these two will be recommended options. Okay, and the various skills you can obtain using your CANSAT or CubeSat project, because it can provide the student with a practical training of whole cycle of a space project, from mission conceptualization, satellite design, fabrication, ground test, and so on. Through this process, the student can know what is important and what is not so important. Also, it is very important as the experience of the engineering, because the student can get a feedback from the real world. That is a very important experience. And it is also good for the education in project management. There are 4 very important management tasks. Please guess. Yes, time, human resource, cost, and risk. Through the practical project, the student can learn how to manage these 4 very important management tasks. So as a result, through my experiences, I can say these factors will also contribute to the other technological areas, not only the space, but also it can be transferred to the other technological areas. And the effect is more than expected. Finally, I'd like to conclude my talk. So please keep this in mind while designing or developing your satellite. Survivability in space is most important. Imagine as many possible failures as you can and prepare countermeasures against them. Reset is an effective way to recover your satellite from anomalies. Please prepare effective ways to do a reset. Start with a very simple CubeSat. After your first success, you can step up to more sophisticated satellites. Study various knowledge skills and project management before starting a development of the satellite. And the CANSAT type hands-on training is very effective. Define the target outcome of your project. Only the launch and operation of your first satellite is not enough. You can get something and continue it to your next project. And finally, so this is, I think, a very important, sense. Have fun. This spirit will provide you with energy, endurance, and never give up mindset. So, enjoy your satellite development. Thank you very much.
Thank you very much, Professor Nakasuka, for the very detailed presentation. I just want to mention again that the presentation is already on the KiboCUBE Academy website, so you can take a look at at it now, and of course download it. And of course, this is being recorded, so you will be able to review all of the content that Professor Nakasuka just explained. So thank you very much. And we're getting a lot of questions, so yeah, I will start addressing them, and we can start answering them. So the first question is referring to one of the first images that you had in your slide. The question is, how do you operate two OBCs on board computers in one satellite? How do you operate two OBCs in one satellite?
Okay, so the how we can operate the two OBCs in one satellite. That is a question.
Yes, exactly.
Yeah. So maybe it's not so difficult. So you can operate as many CPUs in your satellite. So only the limitation is the size and the power consumption. If the power consumption is not so large, you can put as many CPU in your satellite, and these CPU will communicate each other to make a total system management of the satellite. So it's not so difficult to input many computer in your satellite. Okay.
Okay, thank you very much. The second question is about CubeSat development in primary and secondary education. So I think the CubeSat development you mentioned was more maybe towards university level, but for younger levels in primary and secondary education, do you have any guidance on how they could do projects? Maybe a CANSAT project, but yeah, if there's anything.
So I think I know there are many options for the CubeSat, CANSAT for the different level of the expertise. So we have been using the CANSAT for the training or education for the younger generation, like elementary school students or middle school students. In that case, we are not using the electronics subsystem because it's very difficult for them to design electronic subsystems. So we are using the normal component like a structure or for example the balloon or something like that, which is everyday component, and make them do a certain mission. For example, make your flying time of the CANSAT from the top of the roof to the ground at exactly the 5 seconds. And if your flying time is longer than 5 seconds or shorter than 5 seconds, your point will be degraded. So another mission is to make your CANSAT stand up at the time of the landing, or make your CANSAT break a balloon at the time of the landing. So such kind of the mission will be given to the students, and then they will consider how to realize that. It's a kind of the problem solving. So even without utilizing the electronic component, such kind of the problem solving training can also be possible using the CANSAT. Okay, and for the high school student, maybe the electronic system can be designed by themselves. Of course, they need for example 1 year training of the circuit design and so on. But after that, they can design their satellite. So in Japan, already the CubeSat is being developed by the high school students. So if we make such kind of the very proper or appropriate preparation beforehand, then the high school student can develop the CubeSat. So in this way, the CANSAT or CubeSat can be trained for the many level of the students by considering the missions. Okay.
Thank you very much, Professor Nakasuka. I think that was a clear answer. The next question is related to available resources for small satellite systems. So are there any courses or books or websites or anything that you recommend? Or maybe UNISEC has a great document about it, but is there anything that you recommend to people when they start their small satellite system,
Yes.
when they want to study about it?
Yeah, thank you very much. So I think I know we are using as a textbook to the student, space mission analysis and design, SMAD, space mission analysis and design. That is a very thick book, more than 1,000 pages. And that book also has some information about the small satellite. So I'd like to recommend you to, go through such kind of the very big book. And in addition to that, for example, the UNISEC are providing the educational course to develop the CubeSat or other small satellite. And so please contact the UNISEC about that. And maybe that is included in the KiboCUBE Academy. KiboCUBE Academy also provide each subsystem design or space environment effect and so on. Such kind of the lectures will be given in the KiboCUBE Academy. So please refer to that. So, and also you can find several good books. I don't remember the exact name for the development of the small satellite. And so please search for that. Okay.
Okay, thank you very much. The next question is about a computer simulation environment. So when people want to test their satellite digitally before doing the real physical test, do you have any recommendations on a computer simulation environment or some kind of software that you use?
Yes, computer simulation is very important to assure your software's functionality to be implemented on your satellite. And I think I'm not sure about the United States, but in Japan, we are trying to make the open source of the S2E space simulation environment. S2E, that is our laboratory's open source software. And maybe I'm not sure it is written in document is written in Japanese, but some part can be written in English, and so you can find out the site of the S2E from a laboratory, and then try to utilize it as a simulation environment for your satellite. And that is my answer. Okay.
Thank you very much. The next question is about space sustainability. So with all the space debris in orbit, is there a way that you can design the spacecraft so that it takes into consideration this space debris issue and the space circular economy? So this person is asking how they can plan in advance, for instance, maybe by adding a magnetic material so that they can deorbit, or how can you design a small sat to be considerate of these issues?
I think I know. One of the very easy solution is that you launch your satellite in the low orbit, not the high orbit, like less than 500-kilometer orbit. For example, the deployment from ISS, then your satellite will only survive in space for about maximum 2.5 years. So in that case, you don't have to care about being the debris. So I think the one solution is that you will launch your satellite in low Earth orbit. And another solution is that you will implement some thruster system. So our satellite has a thruster system, and at the end of our lifetime, it will emit the thruster to go down to the atmosphere to be burned out. And another solution, as you said, is to put magnetic plate so that, for example, the astroscale can catch your satellite and going down to the atmosphere. So there are several ways, and please check what kind of the thing you can do, and put such kind of the material to your satellite. Oh yes, I remember that another way you can buy some component which can deploy after the at the end of the lifetime, so that using the atmospheric drag, it can go down very quickly to the atmosphere. Such kind of the deployable structure would be another choice. So maybe some company is now trying to sell such kind of the material which avoid being debris. And so you should find that you can find out such kind of the component from the website. And what we did is like that. So we will not we launch our satellite in the low Earth orbit, and we put the thrusters and so on. Okay.
Thank you very much, Professor Nakasuka. And for KiboCUBE, as Professor Nakasuka said, it will be launched into low Earth orbit. But when you apply to KiboCUBE, we ask that you do this analysis on how you considered the space sustainability issue and all of that. So please make sure to look at the relevant guidelines like the space debris mitigation guidelines, long-term sustainability guidelines as well in this regard. Okay, the next question is about the Hodoyoshi system. So what were the most critical problems you had when achieving the main functions of the Hodoyoshi project at the system level?
So what is that? Sorry, would you say it again?
Yeah, so what was the most critical problem you had when achieving the main functions at the Hodoyoshi system level?
I think maybe so we had several critical situation after launch, and the most critical situation is that attitude control failed. Not failed because sun sensors catch the albedo of the Earth. That is reflection of the sunlight at the south pole of the Earth. And the satellite recognizes this albedo as a sunlight, and the solar paddle is directed toward that albedo. Then there was no sunlight is shining on the solar paddle. That means we cannot, the satellite could not obtain any solar power generation, and the battery voltage gets very very low, and it almost died. But by utilizing the magnetic torque to change the attitude manually, and then after, I remember that after 1 week, the attitude goes back to a normal state. That is, sunlight is shining on the solar paddle, solar cell side, and finally it recovered to the normal state. But in this way, maybe sun sensor is very dangerous. It may detect the albedo as a sunlight. And then Hodoyoshi was almost died at the time. So this is what we experienced on the in the orbit. Okay.
Thank you very much. The next question is about the different subsystems. So, which subsystem do you recommend to focus mostly to prevent the early loss of satellites? Of course, all the subsystems are important, but do you think
Yeah.
there's one that is very important compared to others? Or
Okay. Thank you very much. So I think most important subsystem is, as I said before, the center line, especially the receiver system. If the receiver system fails, you cannot send any command to the satellite. So that means satellite will not behave as expected. So you should be you should carefully design the receiver system. So that's why in our Prism satellite, we made a redundant system in the receiver, which has two receiver and which each has a pico processor. Okay, and another very important component is a power system, power electronic system, and the PCU power control unit is very important. And because if there is no power generation occurring in the satellite or power distribution fails, then the satellite will not survive anymore. So these two subsystems is very important. And the main CPU is a third important one. But if we put a small PIC processor or other very simple processor for controlling this PCU or receiver, then that very simple processor CPU will operate your satellite in the very very I can say simple way, and then this CPU will turn on the main computer, and the main computer can do many other things, which including the even sophisticated function like attitude control and so on. But maybe you should make such kind of the very simple CPU, which is very tolerant against radiation in your receiver and or PCU, and which can initially be turned on to operate your satellite. So please, make a very good system for receiver and PCU. That is most important to subsystem.
Okay, thank you very much. The next question is about the deployable antenna design. So this person is asking how much the cold welding phenomena will affect the deployable antenna design. And this person is also asking if you can explain more about the deploying antenna mechanisms.
No, so maybe so. If you put several, surface material on this deployable antenna, then cold welding will not occur. The cold welding occurs when the surface material of the aluminum will be something like scrubbled, and the two aluminum will get together without any surface material. So if you make a how to say, paint on the surface of the aluminum of the antenna, then cold welding will not occur. So in our satellite system, every time we made such kind of the treatment of the surface of the aluminum, then the cold welding never occurred in our satellite. And as to the design of the deployable system, maybe you can utilize metallic measure. The measure to measure the distance or the length of something, and that has a very cross section is called a convex. It is not a flat. It is not a flat, but it kind of this kind of the shape. Okay, and then you can store your antenna in the small volume, and after the release from the rocket, maybe for example, if you put some nylon line which can keep this kind of the rounded shape of the antenna, and after release from the rocket, this nylon line will be cut by the nichrome line, which will be heated by flowing the electrical current, and then this antenna will be deployed. Such kind of the nylon line plus nichrome line is a very effective way to hold your antenna and deploy successfully. And we tried this kind of the mechanism in our satellite more than 20 times, and the 100% success rate. So I'd like to recommend you to do this kind of the hold and release mechanism using the nylon wire and the nichrome line. Okay, and also as to the material of the antenna, I'd recommend you to utilize measure which has this kind of the convex shape. Okay, and we launched such kind of the convex shape measure based antenna. I remember more than 10 into the space, and every time it was very successful.
Okay, thank you very much, Professor Nakasuka. I'll just pick up one last question because we still have many, but one last question.
Mhm.
So what is the optimal battery voltage level required for each different satellite operation mode, such as the sun acquisition mode, the mission standby mode, the mission mode? What is the different level, the different battery voltage level that is required for these different modes?
So yeah, usual how can I say standard battery voltage depend on the how many battery is connected in serial and so on. So it depends. So it's different from mission to satellite to satellite. So I cannot say the standard number as to the appropriate battery voltage for your satellite. But I think I don't think we need to change such kind of the standard voltage of the battery in the different mode. So in each mode you can have the same amount of the battery voltage as a standard voltage, and if the battery voltage gets lower than a certain threshold, so your OBC should do something. For example, turn off some component and go to the safe mode and so on. Or sometimes it should automatically go back to the sun acquisition mode in order to accelerate the power generation using the solar panel and so on. So maybe I don't think we need to change the standard voltage among the different, modes. Okay?
Okay, thank you very much for the very clear answers. I'm hoping that you all see my screen. I'm sorry that we were not able to share the entire we were not able to answer all of the questions, but if you still have any questions, please send your questions to us here at UNOOSA access to space@un.org. Also, you can type in your questions in the questionnaire form, and we will try to address them in a document later on. But thank you so much for everyone to really engage with us and ask many questions. And thank you again, Professor Nakasuka, for the really detailed information and for all the clear answers. So with this, I just want to say that, KiboCUBE, we still have 2 months. We're waiting for your applications, but KiboCUBE Academy is, available through the ear. It's online, it's free. As Professor Nakasuka said, it is a great place where you can start learning about satellite development, and it's really going through the whole life cycle of satellite development, from the design, from the operation, from testing. We have all these different topics. So please have a look, and if you have any ideas or any topics that you want us to do more in KiboCUBE Academy, if you want a specific lecture on it, please send an email to us, and we will definitely be in touch with JAXA and UNISEC to be able to provide you with more information and lectures about that. Okay, so with this, I'd like to thank everyone, and especially Professor Nakasuka, for the webinar today. And we look forward to receiving KiboCUBE applications, but also for us to keep staying in touch. And we hope that we provided good stuff for capacity building in terms of satellite development. So with this, thank you. Have a nice day, everyone. And we'll see you soon. Thank you very much. Bye.